Hi guys, how we doing? Welcome back to another video. So I am going through Introduction to Microcontrollers from a company called Matrix, which is now my employer, and I'm teaching myself microcontrollers using their bit of kit, which is this EBlocks modular learning microcontroller programming thing. So I believe this is lesson 8, and what I'm currently on is, so I'm going through the, are they like exercises? Programming exercises. So I did the first programming exercise yesterday, which was basically writing hex LED outputs. So you can see here I've like done this little animation thingy. So all right, so here's the code from last time where I'm basically just setting a variable for delay and then writing to outputs and delaying based on that variable. Let's start. So I believe we're using delays. In this exercise, you'll learn how delays are used to slow down the PIC. Microcontrollers work extremely quickly. A PIC can execute about 5 million assembly instructions every second. A human can detect and understand only around 3 stable images per second. So to allow the high-speed PIC to communicate with slow humans, we sometimes need to slow it down by adding delay instructions. So I've done all that background. Objectives: add a delay to slow down execution of a program, change the delay interval, configure a delay icon, control the speed of the microcontroller using oscilloscope to time events. So I've already done most of this, so yeah. Begin by opening the program, creating in the last exercise. Add delay icons, configure them so that the output states can be viewed comfortably even at high HS oscillator speeds. Output states can be viewed comfortably. I guess something like, I don't know, 500 milliseconds. Let's just do that. Make that 500. Save the program, download it to the PIC, testing the program on the EBlocks board. Modify, oh, USB not open. What happened? Alright, so that worked eventually. I'm not sure why it came up with an error. Start with a delay of 1 second. Progressively reduce the delay until it's too fast for your eyes to detect the different output states. So we kind of already know what that is. That was around about, I think 50 milliseconds was okay to see. Let's go with 20. So I'm guessing what we're going to do here is we're going to make it so the LEDs go really fast, but then pull out on oscilloscope and use your oscilloscope to look at the output, which is clever actually. I hope we're using the oscilloscope like debugger on this chip, and we're not just going to use the oscilloscope on simulation. That's what I hope, because I'd like to know what's going on here via the software. So all right, we've done that. What's next? Progressively reduce the delay. So again, you can kind of, I mean, you guys can't see properly, but I can still see it enough. But anyways, that should be enough for the purpose of the lesson, right? Download the PIC every time and test it on the EBlocks. Use an oscilloscope to measure the delays you set up in Flowcode. Make a detailed drawing of an oscilloscope image, complete with voltage and time information, and delay time used with Flowcode. I mean, you know, they've just pulled an oscilloscope out here. Like, so if someone in college was learning microcontroller programming, they would now just pull out an oscilloscope and use it. I mean, I don't even know. Like, I have a scope. I didn't know that I needed one for this. I'll use my handheld one because I'm not going to get space on my desk. So, okay, I'm going to use a scope. Use an oscilloscope to measure the delays you set up in Flowcode. How do I do that? Do not test this in simulation mode. Simulation timing is not always accurate because it runs under Windows operating system. Sorry, you guys can't see that. It says do not test this in simulation mode. Simulation is not always accurate because it runs under Windows operating system and not in real time. But how, you haven't given me any instructions on where to plug in. So they want me to chuck in the oscilloscope on here. Alright, hang on. Alright, now I am squarely out of my comfort zone here. So this lovely oscilloscope, I think I have a video on this. I don't know. I bought it like 4 years ago. So I got some crocodile clips. I assume I can't probe whatever I'm meant to be looking at with but yeah, I don't have the right probes for this at all. I have no idea what I'm doing. What am I meant to be looking at? Like, okay, since they've given me absolutely zero. How is a college kid who's learning microcontrollers just supposed to pull out an oscilloscope and measure? I don't understand that at all. What do I look at? Do I look at the... So thinking about this, I guess I'm going to look across the LEDs that are turning on and off. But none of these LEDs are turning on or off every 50 milliseconds. What did I say? Was it? So in the code, I set 20 milliseconds delay. But that is big. So that is port A and B fully on. And then 20 milliseconds later, this one bit turns off. So these are on for 90, like this one here is on for 95% of the time, or whatever it is, 100 divided by 8. So yeah, I don't know really. I don't know what I'm expecting to see here. So I'd expect this pin here to be on, the most significant bit to be on for 80% of the time. But okay, how do I don't know really anything about SMD components actually. So I need to, mate, this is just one big, I was not expecting this at all. They've got me on a Monday night at 1 AM plugging my probes into random places. Don't blame me if I short something out and the board dies, okay? You can't even see my scope view, can you? Alright, we'll try again. So I can see a resistor, so will I get, if I go across the resistor? Okay, so I've got a reading on my scope, which you can't. But now how do I range this? I need another hand. Alright, I need to somehow hold this. It's not like this is a breadboard where I can just plug this into a breadboard. I don't understand I don't get this. I think I'm on a resistor, but I don't know. So auto. Alright, so is it, I have no idea how to use this. I don't even know how to use this scope. I ain't used this in years. Alright, what am I doing? So AC, DC, which one am I? I'm on DC, correct? 10 volts. So what voltage is going to be? It's going to be 3.3 volts, isn't it? So if we go into 5 volt range, 10 milliseconds, 5 milliseconds, so that's too small. 20 milliseconds. Alright, so I'm on 5 volts. I've got something on the scope. I don't know what it means. Why is it such small voltage? I don't understand. I expect 3.3 volts. Alright, so what does that tell you? Firstly, my probes are the wrong way around. I'm going to go on across the resistor on the LED for the most significant bit. I probably don't have a good connection. Alright, there we go. So, you guys can't read the display. Maybe you could just about barely read it. It's an 11% on duty cycle, 89% off duty cycle. Which is correct. I actually did it, you know. I actually did it. I'm a genius. Alright, so then this should, if I go to the least significant bit, so this is the most significant bit. If I go to the least now, then this should be the inverse. Should be 89% on and 11% off. I hope you can hear me because my microphone is actually behind my head there. But alright, let's try again. So again, can you guys even see that scope? Hey! Wait, oh. With my eyes, I can't actually even see what I'm probing. I think I'm on the resistor. Oh, there we go, look at that. So, I don't know why the voltage is kind of sloped. If you know why, please tell me in the comments because I need to learn this stuff. But I have a 16%. It says I have a 17% on and 84% off. Have I swapped the probes again? No, I haven't. But yeah, I mean, that's what the little the display with the text on the left say. But when I look at the actual graph, obviously it looks like the graph is saying that we are 84% on, 17% off, which is about right. And it looks like we're only putting out 1 volt, but I guess that's just 1 volt across the resistor. But yeah, I don't know. Oh, okay. Oh, going across the LED is much easier. So I've gone across the LED there, and now I've got a much better signal. So can I just reduce my voltage? Or increase my voltage range? 2 volts. Hey, look at that. We've got a nice little square wave. Oh, it's gone again. Oh, there we go. Hey, this is cool, man. I'm not gonna lie. You know what? That lesson was trash in terms of just telling me to whack out an oscilloscope. I didn't even know I needed one. Did it even mention in the beginning of the? I mean, I didn't read the whole PDF, but you know, I didn't know I needed a scope, and oh, that was class. All right, cool. That was a fun lesson actually. I think that's the end of that lesson. Yeah. So next lesson we're going to be using connection points. A connection point or go-to instruction is often used to create an infinite loop to repeat a set of instructions over and over. A better way to do this is to use a loop instruction. The advantage of a connection point is that it can be used to jump out of a loop in a certain location in the program. The idea of pulse width modulation is introduced as a means of controlling LED brightness. Cool. All right, that was a nice one. I don't know. I despise how the lesson layout was, and the fact that I wasn't given anything to go with for the oscilloscope. But other than that, greatly enjoyed it. That was actually, it turned out to be a hell of a lot of fun. And yeah, I mean, just another little great buy, this little oscilloscope. Honestly, I was told, actually, I remember, I think if you find one of my videos on my channel, I've got this oscilloscope, and either someone commented or someone messaged me and said, look, don't buy this crap. This crap is useless. You know, it's not useful for anything real. But look, I didn't have to bring out a massive fat oscilloscope and redo my whole setup. Nice little handy one. Cool. All right, thanks for watching, guys. I'll see you in the next one. Take care. Bye bye.